symmetric value of mass m. And this solution can be extended to include a charge very simple way. So the solution looks more or less the same as partial solution, just with another term. As I was telling you yesterday, the addition of this term changes completely the properties of the solution. This is what we're going to do first. So the line element that we have for the Penrose space-time is the Schwarzschild piece, and there is another term, u squared divided by s squared, d squared. explicitly with the geodesics that the only possibility for observing this region is to go all the way until this area, to the region. Okay. So this horizon is simply interpreted as an even horizon. Okay. So it's an even horizon because if you cross this way, there is no possibility for you to go back. Okay. So another day that crossing this region cannot go back, this is why we have a black hole. Okay. So it's the same that happened in the case of the Schwarzschild solution. Once you cross the inner horizon, there is no way to run away from the black hole. But here the situation is different because if you cross the region, the region here, the manifold becomes again time-like to the observer. Okay. So the observer here is free to move in any direction he wishes, particularly can try to go back to the region. So this is not a horizon because it does not force you to move in this direction. You can try to move in the other direction. Okay. This is called usually something called chill horizon or simply linear horizon. Actually, there is a very interesting phenomenon happening here in the inner horizon because of the fact that you can move in this region, you have to move this way, but here you can try to go back. In the 91, 92, when people consider what was happening here, according to this movement, according to the, try to study with types of light rays, what they found is that this interaction between the fluxes of light that try to go this way, and the fluxes of light that try to go back. There is a very interesting procedure, very interesting phenomenon that is called mass inflation. I'm not going to discuss this in detail because it's very complicated and can only be fully understood numerically. But the mass inflation simply means that if you are an observer traveling in this region, back the action that happens between the fluxes of light going inside and the fluxes of light trying to go back, make the local mass that this observer means to grow without bound. Okay? So actually, what people will see, if you are an observer traveling this way, what will you see actually will be a curvature singularity. Because this unbounded growth of the mass induces an unbounded growth of the curvature. The curvature is scalar. So this phenomenon is called mass inflation. And for the decades, people have discussed this numerically in order to see whether this is a true singularity in space-time. Okay. So in this case, you not only have to consider the static solution of the Cohesion constant of space-time, you also consider the dynamical solution where this inner horizon is caused by fluxes of light. Okay. So it's something very, very complicated to discuss. It's not solved yet whether this is really a true singularity or not. Okay. So just going to mention the there are some papers by, I think that the first paper was by Watson and Israel. I think it's the 91. Usually this is quite unknown by it's something it's very interesting, but anyway, ironically, this solution when it's discussed, what you find is that here there is no problem with the curvature. Here is no problem too, unless you consider the mechanical scenarios, but the static is fine. But what is happening here, what is that in divergences? So you can compute the curvature scalars to see what is happening, like in the Schwarzschild case. Yeah?
I'm sorry, do you mind repeating what the mechanism was leading to the singularity? Do you mind repeating what was the mechanism that led to the singularity?
What is happening as singularity there?
Yeah.
Well, it's not clear that this is clear as singularity. It's simply that there are flux, as I said, okay, light can cross this way and can cross the other side. And this interaction between these two fluxes is highly nonlinear. And when there is a kind of back reaction effect that grows as time goes on. And if you are an observer traveling here, and you compute the mass that you are seeing when you are getting attracted by this thing, this mass grows without limit. So the closer you are, the higher the mass you see. And in the limit where you are in the horizon, this mass diverges. And the curvature is related to this mass, and diverges as well. So is this really a singularity or not? Because this is numerical, it's not easy to, it's not clean. It's very, very messy because there are different kinds of reaction effects that you have to take into account. And even the modeling
energy or configuration, whatever. But what is the interpretation of the light rays trying to get out? I mean, where are they coming from? Are they...
No, because the light ray cross this region.
Yeah.
Okay, so light ray cross the region, but in this region, it can move any direction.
Okay. So you mean that the
Yeah,
light...
the light effect that we here can turn the light down again. Okay, because there is no it's not forbidden to go this way. Okay, so you can consider these lights are going to be forced by this nothing to go back and see what is happening here. Okay. So it's the same here. A light ray can move this way or go back. It depends. Okay. In this region, you are free to move in any direction. Here, you can have to go this way. Okay.
Can I ask a question? It's unrelated though. So the measure depends on the square of the charge. So a test charge particle will have the same motion regardless of the plus or minus charge.
This one right here.
Why does it make sense? It doesn't make sense in my mind. So if it's like a big plus charge black hole and a proton, I would expect big attraction but with a slight repulsion because of electrostatics.
Yeah.
And big plus charge black hole with an electron, I would expect even more attraction.
Well, the point is that if you have an electron, a positive and negative charge inside the black hole, they are going to neutralize from outside. The global charge, because remember that the charge that you see is something that you see from outside. So if there is a positive and negative charge, you see a charge as zero outside.
It's sort of not really a charge in a normal sense, is it either? Is it not really a charge in a normal sense? It's sort of a constant of integration of your...
It's a constant integration that arises from the equation of the magnetic field.
Yeah.
This is there is a related... No, make the question.
But so I mean, if you wrote down, say, a charge particle action at the end, you wouldn't have necessarily the same Q interaction charge as you have that Q there.
Yeah, but if you are considering the movement of the charge following the black hole,
Yeah.
to add additional term to the equation
Yeah.
to see how this charge moves.
Yeah,
This is not taking into account because
Yeah,
this
exactly.
charge does not see this. This is something that you see from outside. This is the global charge of the black hole from outside. You don't know exactly how the charge are distributing to the black hole.
So just do some work to show that that's the global charge of the black hole. It's not quite clear to me. Sorry, no, it's fine.
No, it's okay. Actually, related to this, there is a problem which is where are the charges that are, okay, you see a charge from outside, okay, but where are the charges that generate the electromagnetic field? Because there should be some charges inside the black hole. This is a well-known problem in general relativity, which is the fact that people say, okay, maybe all charges going to the singularity, and they are generating the electromagnetic field that is seen from outside. If you try to do this, you will need to get the Einstein equations with a point line charge and delta function at the center. And this is the charge like in classical electrodynamics. Okay, you have a point line charge that generates all the electromagnetic field. If you do this and get the Einstein equations and put a source, a point line charge in the center of the black hole, this doesn't work. The Einstein equations do not give you the Raychaudhuri solution. It's not possible. And usually it's called the source exploring in the sense that if I put a point line particle at the center with all the mass and the charge of the black hole, is that possible? That this is the source of the Raychaudhuri geometry? So the answer is no. Mathematically, it's not possible. You write the Einstein mass equation with a source there containing mass and charge and a delta function at the center. This doesn't work. The equations are not satisfied.
Yeah. So is it perhaps misleading to call that charge?
It's the charge in the sense that it's a long range field and you see from outside. You measure from outside of the movement that you are feeling a force generated by a mass and a charge. That's the only thing you can say. But you cannot say what is happening inside.
So it's got nothing to do with the charge of electrode.
Right, so yeah, because there's no currents involved in that solution, right?
Yeah, if you want, as I said, if you want to include the current and so on, that's the equation and give you this, it's not possible.
Yeah.
Because it's
And the interactions are
Yeah,
not thankfully.
because it came out as like constant integration.
Okay.
Yeah. So is that a stable solution?
well, what do you mean by stable?
As in, as you send a perturbation through it, would it collapse?
If you show the perturbation, it's stable, but the point is that for most of solutions we are Schwarzschild, it has been proved that it's stable. The other solutions, I think that the other solution is unstable number 2 is unstable. And unstable at extremely long time.
Yeah.
Compared to the, so it's stable to all purposes.
Right.
But if you, well, study the stability of these solutions is extremely complicated.
Yeah.
So there are mathematical advanced numerical methods to deal with this, and it's very difficult to cite the problem. But as far as I remember, if you really prove strongly the solution, it becomes unstable, but in very long times. So it's not worth it this way. Okay, so I was saying, like in the short set solution, we can see what is happening at the center of the solution to see whether we have a real singularity. So you can check again the curvature scalars. Okay. So, repeat it everywhere. See what happens at the center, and you find that the scalars diverge. Okay. Like in the case in the short set case, these diverges. In this case, we have well 3 of them diverging. Actually, it's enough with one of the diverging to say that there is a curvature singularity. Okay. So it's the same situation as in the case of short set solution. Okay. So we have the description of the horizons have changed, and the dynamics inside the horizons have changed, but we still have a curvature singularity at the center. And what's happening if this bound is not satisfied? So then it means that you have no horizon. So your metric becomes this way, never touch the zero of the metric, and there are no horizons. Okay? And because we have a curvature singularity at the center, which is naked, which is not covered by any horizon, so this is called a naked singularity. This brings another problem, because in the case of the short set solution, we have a singularity, but it was covered by a horizon. So you could say that you could see that it's a singularity, but a singularity that you cannot see. A singularity that cannot is not causally connected to asymptotic observers. So we are saying we are covered by a horizon. In the case of this Penrose solution, the situation is much more bothering, because even though in a statistical configuration this bound is going to be satisfied always by far, mass square is much larger than the Q square, as statistical black hole. But you could always think on a scenario, theoretical scenario, where this bound is not satisfied. And to satisfy, you have a singularity can be seen by infrared observers, and this is very troublesome. So to deal with this, Penrose invented something that he called the cosmic tensor field conjecture, by which all black holes that are formed out of gravitational collapse are assumed to be always covered by a horizon. It's a conjecture, it was never proved. This is a way to rule out the possibility of naked singularities in nature. Okay? As I said, for astrophysical configurations, no problem, because they are always satisfied. But if you are thinking on scenarios where black holes can be created in the early universe, and that's fluctuations, so there could be small black holes, tiny black holes, where this bound is not satisfied, so you have complete singularity. Okay. So usually, when you have an infinite singularity, you expect the solution of your theory, so it's something, it's a potential trouble of your solutions. Okay. So it's something people are really worried about having this in this theory, how to try to hold out this possibility. Okay, and what happens if the mass square is exactly equal to Q squared? happen. This is called a spin black hole. The spin black holes have a lot of interesting properties by its own. Actually, this is the black hole that people in string theory used to make the computations of the computation of the entropy using microscopic degrees of freedom, all these things. Most of the results about this are based on this kind of spin black holes or near to spin black holes. Okay? But they have a lot of interesting properties that I don't want to discuss because there are many papers dealing with this kind of black hole. Okay? So, more questions about the technical solution? So I'm going to that.
Does it mean that for it's extreme or extreme?
Well,
Does it mean that for those for that kind of black holes, the mass inflation thing is rendering the horizon singular? I got to prove that the mass inflation leads to
Actually, yeah.
real singularity.
Actually, things are much more tricky because if you know something about black holes, there is the relation between the entropy of a black hole and the area of the black hole. Essentially, it's the area divided by 4. So if you have a black hole with a non-vanishing given horizon, like all this, well, it means that the entropy of your solution is going to be non-zero. Your horizon is non-zero. The funny thing is that for the spin black hole, the entropy is exactly 0. Okay. So this is a little bit strange because actually, if you do the calculation from 0, like Hawking did in his papers, and you impose the spin black hole, you get that the entropy of the solution is 0. This kind of big because you have the area law that tells you that the entropy is related to the area. The area is not vanishing, how can the entropy be 0? So the point is that actually they do not compute exactly the same thing. Because even though you think that in the spin black hole the separation between the horizons is 0, they have been approaching, this is confusing, this is misleading, because actually here space-time is time-like, but in the region between the two horizons is space-like. So the meaning of time and space, they are reversed. So when you are seeing this, that the distance is approaching to 0, actually it's not, it's quite the opposite. It's divergent, the distance. The reason is that there is a whole world of topology hidden there, that you don't see directly there, but you have to take into account. Okay? And if you take into account this additional topology, then both the source match. Okay? The discrepance of this source is just explained because you are not taking into account this issue of topology. Okay? It's a paper by Carlos. Maybe 2010, something like that, where he explained this in very nice detail about what is happening here. Okay. So this issue of having mass inflation with the spin black hole is very tricky because what is the solution you are studying exactly? The one with the topology or the one without the topology? Okay. So I'm not sure that anyone has studied this issue of mass inflation in this understanding. So I guess that is going to be extremely difficult to do this. Even in the standard case, it's very difficult. So questions? Questions? I have not much time about to talk about the care and Keltman solutions, just going to mention briefly. So the care, I was telling you yesterday, care is a solution that has many equations where a body has mass and angular momentum. But the point with this is that the derivation is not funny because, well, you saw that in the Schwarzschild-Desden-Doston solution, it's very easy to make the derivation. You just write your line element, staticity and spherical symmetry, and you get the right number of functions as compared to the number of equations, and you can solve it, and that is very easy. But for the curve, things doesn't go that way. Okay? Actually, you have more variables than the equations. You have to impose additional constraints, and the derivation is not very fun. So it takes quite some time to explain. extension of this, which contains the mass, the charge, and the angular momentum, and the same. Okay. So it's also derivation, which takes quite some time. So actually, it took also a very long time to derive these solutions compared to the Schwarzenegger-Desdendos because of this. Okay, just about this. Because this course is more focused on issue of singularities, which is what I'm going to tell you now. Okay. So by far we have seen two different kinds of singularities. Okay. One is coordinate singularity. People in the 40s, 50s were taking this as a real singularity. Now we know that it's not. Real singularity simply means that you are taking the choice of coordinates. So take a good choice of coordinates, and singularity coordinates are no problem. But what happens about curvature singularity? Okay. So those singularities are characterized by the grow-up of curvature scalars. Remember that we were dealing with curvature scalars because you could have a divergence on the different tensor. But this could be not really a singularity because it depends on the choice of coordinates. So maybe this divergence in a different set of coordinates doesn't diverge. But the curvature scalars do not depend on the system of coordinates. So okay, I'm happy with curvature scalars. So consider the teaching. Consider something. The teaching is one. Curvature scalar, the square scalar, and the correction scalar. Okay. So there are more. I don't know exactly how many, but more than 10. Some of them, some of them can be also the variety in terms of the other, and depending on some situations, they can be equivalent or not. Okay. And usually in the literature, you will see that these three are the ones that people usually study. So it looks like a good definition in the sense that, okay, gravitation in Einstein theory is a matter of geometry. Since the geometry is characterized by curvature objects, each tensor, so you can compute objects built out of curvature objects like curvature scalars. If they diverge in some dimension of space, so it means that curvature has exploded. Since gravitation is a matter of geometry, curvature has exploded, so okay, this is a singularity. It looks very intuitive, it looks very natural. But it's plainly wrong, not true. And I'm going to try to convince you why this is not so. But there are several arguments. First I'm going to give you some arguments, and then we are going to show you why the singularity theories do not tell you anything about this. So the first point is that curvature is something where your geometry explodes. Okay? The problem is that geometry is defined on top of that is defined on top of a geometry which has a metric. When the metric has exploded, there is no way to define geometry. So how can you define a singularity at something that is happening at some point on the space where, but in this point on the space, you don't have anything to define the space. So it looks like a game of words that I have no space at the singularity, so I cannot say that singularity is something happening in my space. I have no space. I cannot define it. Okay? It looks like a game of words, but it's not. So by definition, singularity does not belong to the causal manifold. Okay? Because it's out of the manifold. It's like manifold cannot have a singularity is out of the manifold. Okay? You can take a game of words, but so for example, in the Schwarzschild solution, the Penrose solution, you can take one point out. Okay? So servers can move up freely. At this point, how you define your server? There is no metric to define the server. Okay, so Minkowski, in that sense, with one point move will be singular. Obviously, this cannot be in the sense that it is very artificial. I have to move 1 point. I just can make the singularity disappear just introducing back the point. Okay. So to avoid this kind of problems, the first idea is to deal with manifolds that are in extendable. Okay, the extendable simple means that your manifold cannot be extended anymore. In the case of Minkowski with one point above, this is not really a singularity because I can extend this manifold just introducing back the point. Okay, so this kind of examples told you examples of singularities are not valid because they are not extendable. They are not always extended. Okay. Now, so what is happening with this is that with this issue of curvatures, is that in the theories of singularities, which is the only reliable information we have about when a singularity occurs, nothing about curvatures is mentioned. You can read the full theorems, the hypotheses and the developments, and there is nothing at all about curvatures. They do not talk about this, which is funny, okay? Because how can we detect the presence of a singularity without dealing with curvature? But you can just open Wall's book, see the different derivation of the definition of singularities, and there is no mention at all to these things. Okay? Because of this problem related to how to define a singularity as something that blows up in a voided space when you have no space to define anything. Okay? So the theories of singularities follow a completely different path. Okay? This different path is to detect the presence of holes. So I was saying to you before, this idea of holes, the Minkowski will point out, in this case, I could detect the presence of singularity just saying that if I am an observer or a light ray traveling in a geodesic, let's say, you can move freely everywhere in space unless you go to the point where there is this point removed. So if I am a geodesic observer and I find this point, my path in space simply finishes there. Okay? So this is a hole in space. Right? So this idea has nothing to do with curvatures. Because we are in Minkowski, there is no curvature at all. I just take one point out. I am observer moving in this manifold. And I suddenly find a point where my trajectory finishes there and cannot be continued. So this could be a singularity in the sense I have found a hole from where my trajectory cannot follow, cannot be continued. Obviously, in the case of Minkowski, this is not a real example because it's not an extendable. I just put back the point I removed, and then the trajectories of any observer are everywhere well defined. But it gives you the intuitive idea that we are looking for. We are looking for holes. What are the conditions? The question is, what are the conditions under which holes are avoidable in your manifold? Okay? And this is what the theories on singularities make use of. Okay? So to look for this, the theory singularities make use of three conditions. Okay? These conditions can be transformed into different conditions, manipulations, but there are always three. Okay? The first one that is usually good is the existence of a half surface. The existence of a half surface simply means that you are going to have always an even horizon. Okay, so you are going to deal with black holes covered by a half surface. Okay, covered by an even horizon, so it means that there are half surfaces. This condition can be reformulated to include other singularities like the Big Bang singularity. Okay, but since we are not interested in that, so we are going to just focus on black holes. The second condition that these theorems make use is the idea of global hyperbolicity. Global hyperbolicity simply means that in your space-time there is a Cauchy surface. This means that there is some kind of surface that provides good initial data for your problem. There are surface that all occurs made only once in order to continue there. Okay? So you can put always good initial values, good initial value problem to the problem you are considering. Okay? And the third one is something that is called the focusing effect. The focusing effect simply means that there is an equation which is the Raychaudhuri equation. usually all the derivations of focusing effects that with the Raychaudhuri equation, which is something that, yes, a geometrical equation about these objects. Okay? Something that is always important, that always holds. Okay? So this equation, making some manipulations, from this equation, you get something, manipulations, but you will see them on notes, take some time to do this. So tells you that mu is equal to times S mu. This object is here. Simply means that you can write the covariant derivative of this vector. You can split it into some symmetric part and some asymmetric part. Okay, and this object, you call it S mu, and this one is A mu. Okay, and the one that here is this part, the symmetric part of this. You always have this. Okay. So this is for mu being, because the singularity theories usually you study this for time light or null observers. Okay. For time light or null. So it simply means that your vector mu is equal to some constant minus k. So k has to be equal to 1 for time light, physical observer. K is going to be equal to 0 for a null observer, okay, for a light wave. Okay, so this vector here satisfies this condition and satisfies this is a geometrical equation that do not depend on the theory of gravity. Yes, fully electromagnetic properties of the tension. Okay, this is this. So the focusing effect in the theorem, in the singularity theorems, tells you that something that is called expansion. Okay. Expansion is defined as the covariant derivative mu. Okay, so it will be simply S mu. Is it? Okay, because it has going to be symmetric. Okay. So this is the expansion. From this equation, what it tells you is that in the expansion is going to be negative. Theta is going to be negative because of this equation. This equation tells you that R or mu has to be greater than 0. Yeah. So this is the formula. Okay, so because of this equation, which is a geometrical identity, the sign of this expansion to be negative, it means that this has to be positive. Okay, and what is the point? That this sign of the expansion is interpreted like if you are defining a body, like a set of geodesics that is traveling together. Okay, so they are only traveling in a geodesic path. This sign, this object going less than 0, means that these geodesics are going to converge all of them to some point. And at this point, this is called the focusing effect. Okay.
Here, maybe I need more coffee. It's not theta dot.
No, it's not.
Sure. Yes.
What?
On the left hand side, you have something like
Here,
theta
this is the
dot.
derivative, you mean, of theta, yeah. Here is the derivative. Theta was lambda is the affine parameter. Okay. In the case of time-line geodesics, so you are a physical observer, this is the usual time. Okay. But if you are a photon, then you cannot interpret as time, so it's an affine parameter that is measured by the geodesic of the photon.
is always negative. Well, it's always positive. Yeah, it's always negative. Right? So the sign, what counts is the R mu nu, Q mu U. And then it's not. Yeah, that's why I think that it's not a theta dot. No, I think that's correct, but it's not a theta dot smaller than 0, provided that. Or is that you are integrating?
But whatever you mean.
No, it's just
Sorry, I couldn't quite follow global.
So global hyperbolicity simply means that you are going always to have in your space-time a surface that allows you to give initial data value to your problem. So it means that the evolution of your problem is going to be unique. Okay? It simply means that. It's a technical definition of what is that, but it's the physical power space. Okay. So these three conditions together give you the Penrose singularity theorem. And the Penrose singularity theory tells you that if you have a manifold that contains a type surface, global hyperbolicity holds, and the focusing effect is present, but you have this condition on the relation. It means that your dialect and your geodesics, they are going to finish at some point, either in the future or in the past. Okay? So the meaning is that if you are a free-falling observer or a null light, which is inside a black hole, your path in time is going to finish at some point, okay, at the affine time. So it means that you are always going to find a hole in your space-time. Okay? So there exists at least one geodesic that finds a hole in space-time. And the mere existence of a single geodesic finding a singularity, it means that your space-time contains a singularity. Okay? So because the trouble with these singularities is that if you are a light ray, it means that information transmitted by light rays can be created out of nothing or can disappear into nothingness. So it means the breakdown of predictability, okay, because information could go out from nothing. So how can we predict this? How can we predict things if we allow things to disappear from the environment? If you are in a physical observer, it doesn't mean that you are simply going to be crushed by a curvature singularity. It means that you simply disappear from the environment. There is no way to define you anymore.
If I have a manifold, I take a point out, and I leave, and I don't leave a boundary, then I can approach that without ever finishing it. So if I have a sphere and I remove a point, that's the same as an infinite plane. So I can get ever nearer that singularity without ever touching it.
That's it.
Sorry. If I have a sphere and I take a point out, then topologically it's the same as a plane, infinite extent, which means I can approach that point and never ever reach it because it's not a bounded part of the manifold. So you can have holes that don't have trajectories ending or beginning at. Is that
You mean cosmic with one point move?
Yeah.
Yeah, but I was saying this is a say. Cannot be resolved that way. It's not something that you take out some region and then you are a geodesic and found this hole and disappear. Because this hole has been already filled. Inside the formulation of the theories, it's assumed that all holes that are artificially removed can be introduced back. The problem with the Schwarzschild solution or the Penrose solution is that these holes have not been removed from the singularity, from the manifold. Okay?
Right.
And holes that cannot be reintroduced back again. So the manifold is completely standard at that
So you're not actually changing the manifold.
Sorry.
Sorry, I don't understand.
Okay. Let me tell you this. See? So one way to avoid the singularities is that this condition here, because of the Einstein equation, this condition is fully equivalent. So it's fully equivalent to this condition of by the Einstein equations. This is the energy of tension, okay? Because of the Einstein equations. Point with this is that there is a immediate interpretation where this that. This tells you these are energy conditions, okay, that are imposed on the matter. So these energy conditions, if you assume an energy momentum tensor that it has the form of a perfect fluid, so flow okay, to assume a perfect fluid expression for this, and you have when you impose this condition upon this, so you can impose some conditions upon the energy density and the pressure of the fluid. Okay. So there are several classifications in the literature about different energy conditions and what is the meaning of this. And this condition, in particular, is what is called the weak energy condition. Okay. So it's the weak energy condition. Okay. This is what is expressed here. And this energy condition, it means that if you have a vector which is time-like, okay, so the energy density has to be greater than 0, and the addition of the energy density plus the pressure has to be greater than 0. Now, the energy density is greater than 0 positive is a completely reasonable condition. So this condition, the Focus effect, in singularity theories, the case of GR is fully equivalent to the energy condition, to the weak energy condition. Okay. Actually, if this vector is instead of the vector is a null vector, then you have the null energy conditions. Okay. And there are different energy conditions about this. Okay. As far as we know, classically, this condition is always satisfied. Leaving aside quantum effects, that's not a different business, but classically, this condition is always satisfied. So it means that if you want to avoid this conclusion of the theories, trying to overcome this condition, the only choice that you have is to assume that your energy momentum source does not satisfy this condition. Okay? So it means that in order to avoid this conclusion of the theories, you need to consider matter violating energy conditions. Okay? And this is why this result is always found in the case of linear relativity, because you want to remove a singularity, which is something we don't like, but you do it at the cost of removing energy conditions that, as far as we know, they are always satisfied in nature, classically. So, the outcome is even worse than the result. So now, if you want to make the Schwarzschild solutions irregular, you can extend it mathematically just passing another Schwarzschild manifold on the other side, but with reverse sign of the mass. So the mass has to be negative. Right? So you are violating energy condition on that side. That's the only way you can remove the singularity, because you are taking this condition out. Okay? But then you are where in the universe do we find sources that violate this energy condition? Classically. Let's say quantum is a different issue. Okay? So this is why these theories are so strong in the case of so these conditions, the three conditions do not depend on the theory of gravity, they are completely general. But in the case of Einstein theory, they are fully equivalent to the energy conditions, and this is why it's so difficult in the case of ER to find examples where you violate this conclusion of this theory. Anyway, people have looked very hard for solutions where these conditions can be violated. I will also discuss this. So, we are going to do this explicitly in the case of Garcia to see how these theories in the case of Schwarzschild leads you to a singularity of this case. Okay? So how you find, how you unavoidable find a hole in your trajectory in space-time, okay? In the case of Schwarzschild. Okay. So to do this, you have to remember how to describe define geodesics here. Okay, so for a given connection, the geodesics in your space-time, which are close to well, you know that there are two different kinds of geodesics. Okay, one is the curves minimal length, and the other thing are curves that are parallelly propagated along itself. Okay, one thing is associated to the method, and another thing is associated to the connection. In the case of ER, both things coincide because the connection is given by the list of residuals of the method. Okay, but you could have a theory where these two things are different. Okay, so the straightest line in a theory of gravity could not be the line that minimizes the proper time. It seems a little bit weird, but there are examples where this happens. But in the case of ER, there is no problem, because all things give the same result. So lambda is a fine parameter. So the geodesics follow this equation. Okay, so this is the equation for geodesics. Okay. This equation can be derived from an action of a particle. Okay, simplify this way. Lambda mu lambda x mu. Okay, so this is the equation, the action for the movement of a particle. The initialization of this action gives you the equation of geodesics, one way of deriving this. So consider a spherically symmetric and static line element. Okay. So we are going to do as general as possible. So we consider a static spherical symmetric metric because we are looking for geodesic in sources, but it's also valid for the vertex with the same symmetry. So you can write for this metric, as we already know, a line element, which is composed of two different functions. The function of r, g squared, plus b r, dr squared, plus r squared. So we have this diagram, okay, spherical symmetry. Okay, so for this spherical symmetric line element, you can model the action. Simply one half lambda r squared plus 1 over b squared plus r squared dot squared plus r squared square theta. Okay, so just dot sample dot derivative of the plus. So this is the action for this particle for static spherical symmetric line element. Okay. With this, you can compute the momenta associated to dr theta phi. Okay. Just standard definitions of pt is going to be minus the partial Lagrangian with respect to t prime. This is going to be minus dot r. So dr minus r. R dot right by r dot. In the geodesic equation, you find that r dot mu, which is the derivative of the Hamiltonian, right? With respect to p mu. P mu is also find the same way, which is going to be just pi x respect to general the momentum defined this way, respect to x mu. So this is minus 1/2 pi mu, the alpha beta, the alpha is beta. Okay, these are the definitions. For these definitions, this follows b dot b equal to b equal to 0. Okay, just making these computations, taking into account that you are in a spherical symmetry and static solutions. Okay, so the fact that two derivatives of the two of the derivatives of the moment are equal to 0, it means that in your spherical symmetric system, static spherical symmetric system, you have two constants of motion. Okay. This constant of motion comes from integrating this equation, means for your metric, ut is going to be derivative by lambda c of r, and we are going to say this phi r squared sin squared theta. This is another constant equation of constant motion. If you are with a time-like observer, the interpretation of this E is the energy density of the particle per unit mass, and L is the angular momentum of the particle per unit mass. Okay. If you are with geodesics, this interpretation cannot be obtained, but you can show that the geodesic movement of the particle depends on the ratio between L and E. This is called the impact parameter. So, if you are in the Schwarzschild spacetime and want to describe the movement of a particle that is traveling around the black hole in a geodesic movement, so this is a very nice and large discussion about how a particle can be swallowed, deflected by the black hole, etc. This is if you are outside the horizon, but we are interested to see what's happening inside the horizon. Okay. Another thing related to this is that you can also see that the Hamiltonian can be written this way. Okay. Square divided by c. r squared divided by r squared minus y squared divided by r squared squared. That means because of these quantities of motion, this can be written minus energy density divided by c minus r dot squared divided by b minus l squared divided by r squared. Okay. You can also descale the Hamiltonian, because this is very convenient. Okay. So the Hamiltonian can be descaled just from getting the affine parameter. You're defining like lambda divided by square root of 2 absolute value of h. And this is done because when you do this, the Hamiltonian can only take 3 values. 3 of the intention values. These 3 intention values depend that h is greater than 0, h is equal to 0, or h is less than 0. 1, 0, minus 1 corresponds to time-like null or space-like geodesics. Okay. After all this discussion, that's finally can write the geodesic equation for this line, for this metric, using all of these equations here. Then I identify that C over B dr lambda squared squared minus C r over r squared plus A. Okay. So this is the geodesic equation that comes from a static spherical symmetric method of this kind to independent functions C and B, because we are not assuming anything about what these functions are. And you get this. There are two conserved quantities of motion here. Okay. This case tells us what kind of, if you are dealing with time-like, null, or space-like geodesics. Okay. Okay, so now we want to see what is happening in the Schwarzschild case. Okay, so this is completely general for any static spherical symmetric metric. And we want to know what happens in the Schwarzschild case. The Schwarzschild, because of this line element, we know that C is 1 minus M over R, and B, and this is equal to B. Okay, same as. Okay, so these two functions cancel each other. So you have here squared, A squared, minus C, squared, R squared, that's cancelled. Okay, so this is the geodesic equation for the Schwarzschild space-time with C given by this function. Okay, but you can write this equation in a different way. So you have something which is E squared minus something. So if I say that this is E squared, this equation is nothing but the movement of one particle, one-dimensional particle, in a potential given by this. Actually, this is how you describe geodesics in the Schwarzschild case. Just comparing this potential, depending on the geodesic you are, with this value of the geodesic to see what is happening, to see whether particles are deflected by the black hole or they are going to be swallowed into the black hole. Okay. So this is the equation that you describe the Schwarzschild case, no matter whether you are outside the horizon or inside. And we are going to see that this horizon, this geodesic equation, leads you to a singularity at the center of the black hole. Okay.
Here, maybe I can start one. You also need radial.
So
You also need radial geodesics.
not only the idea.
So is there any other equation for the theta evolution?
For the theta.
Yeah, why are you assuming constant theta?
What do you mean? Ah,
No, this is a
Yeah,
this is a equation only for other radials.
yeah, but the angular momentum contains whether they are with radial or not radial geodesics. The information of this is contained here. If you take put L to be 0, then it's radial geodesics. Otherwise, it's a geodesic with angular momentum. Based on information about the angular circle is contained here. Okay, so we want to see what is happening inside the horizon. The first thing we need to make sure is that observers that have crossed the horizon have to go to the center of the black hole. Okay, this can be proved in a very easy way. So again, Edison Finkelstein coordinates that we were discussing yesterday. Okay, we can define these coordinates for this line element to be something like this. So it's dt plus r divided by 6 plus 1. We define Edison Finkelstein coordinates this way. So you have your line element because this minus c r squared minus dr squared goes on, which means that dv is 0. You must have that this equation tells you, okay, this equation of b, so this is everything here is positive, so it means that the r has to be greater than 0, assuming that ds squared is positive. Okay, if ds squared is positive or greater than 0, so it means that the r has to be less than 0. So if you are a physical observer or a photon that is inside the horizon, as time goes on, your radius has to decrease all the time. Okay? And since there are no more regions inside the horizon, you only have the choice to your radial coordinate describing your movement to go to the center of the platform. Okay? So it means that if you cross the horizon, if you are a photon or a physical observer, an observer, your only choice is to go directly to the center of the solution. Okay? So in the Schwarzschild case, there is no other option. In the Raychaudhuri case, because this function changes sign, because they are in the horizon, you can change signs again, and there is the option not to go to the center of the solution. You can go back to the inner horizon. Okay? In the Schwarzschild solution, there is no other option but to go to the center of the solution. Okay? And to see what is happening at the center of the solution, now we have established that you only have this choice, so you want to know what happens to your affine parameter using the geodesic equation. So it's enough to see what is happening at in the case where there is no angular momentum, so L equal to 0. So we have this equation, we have L equal to 0, equal to n squared minus k minus 0. Okay, so this is the equation. Okay. Because this term diverges, if you are with kappa equal to 1, okay, so you are with a fine life geodesic, okay, which is kappa minus 1. This is a fine life geodesic. This term is going to dominate over the energy density because C diverges, okay, so this is the dominating term. And when you integrate the geodesic equation, you make this. So you get that PR lambda is approximately at the center of the solution goes like square root of 2f divided by r. Okay, when you go to r, equal to 0. Okay, because this term dominates over this. Okay. Let's essentially just put this function here. Okay, so this term is going to dominate over the 1. So you have this thing, and taking the square root, you get this.
Sorry, is the minus sign inside?
Well, there are two equations. Okay. See this. So if you integrate this, you want to get lambda as a function of r. So you get lambda of r. It's going to be some constant. It tells you the initial instant where your time like observer is starting, the thing. You get that this is 2/3 of the square root of here and 2/3 divided by okay, so this is the equation. Okay. So when you go and are going to 0, okay, so this is the initial instant, and you taking let's see this. So it's finite. So it means that your affine parameter that describes the trajectory of the time observer, when you go to the center, it gets a finite value, and it is over here. It cannot go any farther. The solution is defined only up to r equal to 0. And the affine parameter tells you that at this point, your affine parameter is finite. At this point, it's not defined any longer. So the geodesic is incomplete. Okay. So this is the result.
You're assuming the point r equals 0 is in the manifold.
So
You're assuming the point r equals 0 is in the manifold.
well,
R equals 0.
can be approached
Right, yeah.
on this. So it means that your affine parameter, which is always finite, tells you the trajectory extend any longer. The trajectory of the particle gets there without no possibility of further continuation. It doesn't mean that you get there and continue all the time. No, geodesic is there. Okay? The geodesic are incomplete, and it's enough. So this is what the theory tells you. The Schwarzschild solution satisfies the three conditions of the singularity theorems. And the singularity theorem is that there is at least one incomplete geodesics. This is incomplete geodesic. Okay? Because there is no possibility for the station. So you essentially have the trajectory of the particle as far as the maximum far. So this is the center of the solution. So this is lambda 0. And this is the trajectory. You are following this way. At this point, it's over. There is no possibility of more trajectory. Okay? So you should have something like, something like this or this or from this to continue your trajectory. In the Schwarzschild case, this is not possible. You always met a singularity, and this function you cannot go any longer. The solution is only defined at this point. In the maximally extended symmetric solution as a solution where you pass another Schwarzschild solution on this side, then you can continue. And this is because you are violating one of the conditions of the energy theorems, which is the fulfillment of the energy conditions. Okay? So in the Schwarzschild case, with positive mass, your geodesics finish here. But this is incomplete geodesic. Okay? And the reverse of this statement is that for space-time to be complete according to the singularity theorems, the space-time has to be geodesically complete. Okay? So the space-time singularity theorems tells you that if the three conditions are satisfied, you always get a complete geodesic in your space-time. In the rest of the case, even though you can try to go back to the initial point, you can also show that there will be always geodesics that meet the central singularity. This singularity, they cannot extend any longer. The trajectory is there. Okay. So this is why the Schwarzschild solution is singular. It's not because the curvature explodes. It's because it contains incomplete geodesics. Okay. The fact that the curvature explodes has to do with the tidal forces that the observer will feel as you approach the end of the complete path. But that's a different concept. But here there is nothing. You just have you have some space-time where you are computing geodesics. You could also say, okay, I can also compute curvature scalars and they also blow up. Okay, so that's clear. They blow up curvature scalars. Why is explanation about why you have found an incomplete geodesics. But this is not present in the singularity theorems. There's nothing about this. So there is no guarantee that this is going to happen. So the fact that it happens in the Schwarzschild solution or in the rest of the solution that you have incomplete geodesics and also curvature scalars doesn't mean that this has to be an unavoidable feature of your theory. Your theory could contain a curvature which is perfectly well defined, no problem, but there is still incomplete geodesics. Okay. Actually, about the singularity theorems, the things are much more tricky because the singularity theorems only deal with geodesic observers. So it tells you that there is a singularity for geodesic observers. But what happens if your space-time does not contain incomplete curves? What happens if all your observers are always geodesically complete? It doesn't mean that there is no singularity. Well, the answer is no. Actually, there are Tory examples where the curvature is perfectly well defined. Geodesically, free-falling observers and null-tides find geodesically complete space-time, no problem. But tiny physical observer, which is in acceleration, for example, because you are in a rocket ship with bounded acceleration, depending on how this acceleration is, you can find geodesically complete space-time or not. You can also find that there are incomplete paths. So all geodesic observers are complete, but an observer in a spaceship with a rocket, depending on how the acceleration decelerates, you could find some hole in space-time. And this is because the singularity theorems only tell you sufficient conditions for the existence of a singularity. So if there is a geodesically complete curve, you have a singularity. But if you have geodesically complete space-time, it doesn't mean that your space-time is regular. There could be curves that are still singular. Not geodesic curves, but other kind of curves. Okay, so actually this is known since the 60s that this kind of examples exist. There are also, as I said, 20 examples, but something that, okay, things are much more tricky than it seems. So it means that in order to make sure that your space-time is regular, first one needs to check geodesically complete character. But there are other criteria that have to be used. One of them is related to tidal forces. Okay? See, because you are obviously the fact that the space-time is not complete is only shown in the sense that the trajectories of observers fields. But anyway, if your space-time is geodesically complete, but a physical observer is of finite size, if the tidal forces, because of the curvature grows large, can be arbitrarily large, what is happening to observe? It can be distorted. Okay, classical. So, when you say that your space-time is geodesically complete, is regular, it destroys observers anyway. Okay. So this is something that we are going to see next day about what happens with tidal forces. Okay, and the destruction of observers. I just wanted to get to this point because in 1 hour I'm going to talk about this in the seminar. Okay. So I don't know what time it is, but we enter into the tidal forces. Yeah, so I think we are going to stop here, and I hope to see you in the seminar because I'm going to play with all these concepts to discuss all my